Hello students, this is our second lecture for optical communication. In the previous lecture we have studied block diagram of optical communication, how many blocks are there and what is the importance. After that we studied electromagnetic spectrum, where we see where the optical communication exactly comes and what is the wavelength range and frequency range. And we also see there advantages and disadvantages of optical communication and how optical communication is more better than as compared to copper cable. Apart from that, we also see different applications where optical communication is used. Now, in today's lecture, what we will see? We will see electromagnetic spectrum again, but this time with some examples. Then we will see optical window. Optical window is nothing but how your optical fiber system, complete system with sources, detector and fiber evolve. Then we will see total internal reflection, how we can achieve a complete reflection or a complete power of optical light inside a fiber with or by reducing some losses. Refractive index, some definitions are related with total internal reflection, that we will see here. Refractive index, Snell's law, critical angle, acceptance angle, numerical aperture. And after going through this all, refractive index, Snell's law, critical angle, acceptance angle and numerical aperture, by the definition and formula, we will solve one example and after that skew rays. Let's start. Electromagnetic spectrum. Here you can see that for different types of frequency, the medium will be changed and the application will be changed. For telephone, AM broadcasting, aeronautical, submarine cable and navigation, the range is from 1 kilohertz to 1 megahertz and the medium we are going to use will be wire pairs. After that, we will use coaxial cable for TV, ultra high frequency TV or mobile or for FM. The range is from 1 megahertz to 1 gigahertz. Then comes waveguide. The range is from 1 gigahertz to 100 gigahertz. And then comes optical fibers, which comes under infrared region. Application will be telephone, data and video, and the frequency range is from 10 raised to 14 hertz to 10 raised to 15 hertz. Next, evolution of different generation optical network. You can see here on x-axis the years are there and on y-axis the system performance in GB per second kilometer. As you can see here, from 1974 to 1990 how the system is evolved. From 74 to up to 77, the wavelength range is 800 nanometer and the system performance is up to 1 GB per second. Then after that, with the development in sources, detector and fiber, we are able to increase the wavelength and able to increase the system performance up to 100 GB per second. Similarly, we can see here up to 90s, the graph is represented here, 5 GB per second for 233 kilometer system with 5 optical amplifiers. Now, optical window. There is an important question from Mumbai University exam point of view. The window is nothing but it represents how your optical sources, detector and fiber fabrication technique is evolved. Okay, so in 1970s, you can see the first window where attenuation is very high. It is 100 decibel per kilometer. Okay, and the wavelength is in between 800 to 900 nanometer. Now after that, with development in sources, manufacturing technique and with fabrication technique, we will add some impurity in silica. Why we will add? To improve our refractive index. In next slide, I will show you what is refractive index and why it is important. But here, with improvement in refractive index, our attenuation will be low. Okay, to reduce that we have to work on sources, detector and fiber. The second window comes at 1300 nanometer and the third window comes at 1550 nanometer. Total internal reflection. It is nothing but trapping light in the fiber. You can see here the two figures are there. The first one where you will see the 4 different rays in red color. One ray is going outside the fiber, one is reflected slightly with slight angle, another is in parallel with core cladding boundary, and after that one ray is completely reflected inside the core. So when we will achieve these 4 rays, when our angle will change, that we are going to see in the next slide. And in the second image will give you an idea how to analyze reflection, refraction and where to analyze reflection and refraction. So you will get the idea that we are going to study light comes outside, from outside to core, that is a different part, and light is reflected inside the core, that is a different part. In the second image at right hand side you will see core, cladding, buffer and jacket. The buffer and jacket, as I already told you in first lecture, is for protection purpose. There can be n number of layers will be there. Okay, so let's move ahead. Refractive index. Refractive index is nothing but speed of light in a vacuum. It is a ratio of speed of light in a vacuum to the speed of light in that medium, C by V. Therefore, the refractive index for air is 1, for water 1.3, for glass 1.5 and for diamond 2.42. The very important thing is here is that our refractive index of core should be greater than cladding. Why? Because as you can see here, for air it is 1. Means what? For air the speed of light is 3 into 10 raised to 8. Means in the formula the denominator and numerator both are 3 into 10 raised to 8. You will get 1. When you will get the higher value of refractive index, when your V will become low. So we will work on how to decrease V. How to decrease V. At that time your N will increase. Means what? Your speed in the dense medium will decrease. Okay? Now Snell's law. Snell's law is nothing but it is a relation between the refractive index of two medium and the light incident with that medium incident with the boundary. Okay, the angle. So Snell's law gives you the relation between the refractive index of two medium and the angle of incidence and the angle of refraction of light. So here you can see that 3 figures are there. In figure A, there are 2 materials are there. One is below the reference line, it is a glass of refractive index N1, and above is the air of refractive index N2. The incident light forming an angle phi 1 and the exit rays forming an angle phi 2. In figure B, when we increase the phi 1 at a point where exit ray is exactly parallel with the boundary, that incident angle will be called as critical angle. And in figure C, you will see when we increase the incident angle beyond critical angle or is greater than critical angle, you will achieve total internal reflection. So what is your Snell's law? N1 sin phi 1 is equal to N2 sin phi 2, or sin phi 1 by sin phi 2 is equal to N2 by N1. Critical angle, as I already explained you in the previous slide, what is critical angle? When your incidence, when your refracted angle is 90, when your refracted angle is 90, here you can see that theta 2 is your 90. When we will put theta to 90 in Snell's law, at that time, what will be our expression? Sin phi 1 by sin phi 2 is equal to n2 by n1, but sin phi 2 is 90, means sin 90 is 1. Therefore, your sin theta is n2 by n1, or your critical angle is sin inverse of n2 by n1. Acceptance angle. It is nothing but based on purely geometrical consideration. It is the maximum angle of a ray hitting the fiber core which allows the incident light to be guided by the core. So in figure you will see here two rays, ray A and ray B. For ray B, the ray B goes inside the core, and after intersecting with core cladding boundary, it's refracted out or eventually lost by the radiation. Why the ray B is lost, and why ray is completely inside the core and traveling its path? Because the angle of ray B with reference is greater than theta A. You will see here the cone. That cone is nothing but acceptance cone. Means whatever light you want to transmit, that light should be inside this cone. And that angle theta A is called acceptance angle. Numerical aperture. Numerical aperture is nothing but it's a relation of acceptance angle with 3 refractive index. What are the 3 refractive index? Refractive index of air N0, refractive index of core N1, and refractive index of cladding N2. So numerical aperture is light capturing ability of your optical fiber, and it is a relation between acceptance angle, refractive index of air, refractive index of core, and cladding. Now this slide is very important. You will see in the above figure, inside of fiber a one triangle is there. Okay, right angle triangle ABC, and the refractive index of air is N0, of core is N1, of cladding N2. There are two angles, theta 1 and theta 2. So we will apply Snell's law in between air and core. At that time, what we will get? N0 sin theta 1 is equal to N1 sin theta 2. Now from the right angle triangle, we know the addition of all the angles of triangle is 180. Therefore, phi will become pi by 2 minus theta 2. Now, what we will do? We will replace theta 2 of equation 2.3 by 2.4, and sin pi by 2 minus theta is what? Cos theta. Therefore, we will get equation 2.5, n0 sin theta 1 is equal to n1 cos phi. Now, with the help of trigonometric relationship, sin square phi plus cos square phi is equal to 1. Therefore, we will replace cos phi in equation 2.5 by 1 minus sin square phi. Okay, and cos square theta square will go in at right hand side, and you will get square root of 1 minus sin square phi, which is presented in expression 2.6. Then, as we already know, the critical angle sin phi c is equal to n2 by n1. So when the limiting case for total internal reflection is considered, phi becomes equal to the critical angle. Therefore, we will replace this sin square phi by sin square phi c, and we will put the value of sin phi c, which is n2 by n1. After that, what we will get? N0 sin theta a is equal to square root of n1 square minus n2 square, and this is nothing but the definition of numerical aperture. As I already told you in the previous slide, numerical aperture is relation between acceptance angle, refractive index of air, which is N0, refractive index of core, which is N1, refractive index of cladding, which is N2. Therefore, this is your numerical aperture. Na may also be given in terms of relative refractive index difference delta. Sometimes another parameter delta n, n1 minus n2 is referred to as the index difference. And relative refractive index difference is represented by n1 square minus n2 square upon 2 n1 square. And if your index difference is less than 1, we can write down delta as n1 minus n2 by n1. Now, in the previous slide, the Na is what? Square root of n1 square minus n2 square. We will replace that n1 square minus n2 square, and what we will get? 2n1 square delta under root. By replacing that, what we will get? Numerical aperture Na is equal to n1 square root of 2 delta. Now, which type of formula? How many formula we studied today? 5 formulas. Index of refraction, n is equal to c by v. Snell's law, n1 sin theta 1 is equal to n2 sin theta 2. Critical angle theta c is equal to sin inverse of n2 by n1. Acceptance angle sin inverse of square root of n1 square minus n2 square. And numerical aperture Na is equal to sin theta a or n0 sin theta a. Here n0 is not represented because refractive index of air is 1, or we can say Na is square root of n1 square minus n2 square, or we can say Na in terms of relative refractive index difference, n1 is square root of 2 delta. Now one example depend on these formulas. You can see here in this example core refractive index is 1.5 and cladding refractive index is 1.47, and what we have to determine: critical angle, numerical aperture and acceptance angle. We put all that formulas and values, and phi c is 78.5 degree, Na is 0.30, and acceptance angle is 17.4 degree. Hope in this video you will get the complete idea about optical window, evaluation of our network, optical network, electromagnetic spectrum with the help of examples, total internal reflections, Snell's law, critical angle, refractive index, acceptance angle, and you will solve more problems at home to improve your problem solving skills. Thank you very much.